Hey, good morning, everyone. Thank you for coming to the Center for Clean Water Technology monthly seminar series. I'm Cheng-Shiuan Li, a research scientist from the center. Before I get started, I just wanted to remind you we have this seminar series on the first Monday of every month at 11:30 a.m. If you missed our previous seminars, you could visit our website and find archived presentations there. Okay, so today I will be presenting a per and polyfluoroalkyl substances, PFAS, testing facility at the New York State Center for Clean Water Technology. So I'll talk about the challenges in detection and water treatment. I believe many of you have already heard of PFAS from news, internet, or from this recent movie, Dark Waters. So this movie is actually talking about PFAS pollution in the US. And honestly, I haven't had a chance to watch it yet, but I'm sure it must be worth watching. Yeah, please watch it. So in today's presentation, I will briefly talk about the general knowledge of PFAS first, where we can find them and their toxicity effects, and the challenges to detect them in the environment. And I'll show you our capability to detect them, and also talk about what treatment methods we can use and our ongoing researches. PFAS. Okay, so what are PFAS? They are a group of man-made organic compounds, and their feature is that multiple fluorine atoms attached to a long carbon chain with a functional group at the end, like this. So here you can see two examples. They are the most researched PFAS compounds, PFOA and Pfos. Okay, they are both like C8, A carbon on this long carbon chain. So carbon fluorine bond is one of the strongest bonds in the universe. Therefore, they can have a great thermal and chemical stability, and they're used to make products that can resist to heat, oil, grease, and water, and have been manufactured and used in a variety of industries since the late 40s. It's been a long time. So in the past, we used to use PFC to stand for perfluorinated compounds. However, PFC is also used to mean perfluorocarbons, which are greenhouse gases and are a completely different group of chemicals. So to avoid any confusion, so today we use the term PFAS to represent this specific group of chemicals. Okay, and there are more than like 4,000 PFAS compounds in the industry. And many of them actually have similar structure, but have different carbon chain length. For example, for perfluorinated carboxylic acid, so we can have C4 compound, PFBA, C8 compound, PFOA, and up to 14 carbons or even more. And same thing for perfluorinated sulfonic acid. We have like short chain and long chain compounds. And the longer carbon chain, the bigger molecule. Their chemical and physical properties could change a lot depending on their carbon chain length. Okay, it can be very, very different. Okay. And where can we find PFAS? Like I said, they are in many commercial household products, including like stain and water repellent fabrics, non-stick products like Teflon, and cleaning products and firefighting foams like this. I'll talk about this later. And you can also find them in workplace, including like Teflon production facilities or industries like chrome plating and electronic manufacturing plants. And they're also in food packaged in PFAS-containing materials, food processed with equipment that used PFAS, or food grown in PFAS-contaminated soil or water. And at last, they can also be found in your drinking water, typically localized and associated with a specific source like landfill, wastewater treatment plant, or firefighter training facility. Okay, as I just mentioned, the firefighting foams, or we call it AFFF, is a highly effective material against hydrocarbon fuel fires. and it is used in airports, fire department, and military facilities. And AFFF actually contains high amount of PFAS. It's like a cocktail of PFAS compounds. And it's a major source of groundwater contamination at airports and military bases where firefighting training occurs like routinely. And because PFAS compounds, they are stable and persistent, they are very difficult to degrade naturally in the environment. So some people call them like forever chemicals. So this figure shows the PFAS cycle. So you can see they can transport via atmospheric transportation, and they can enter surface water and groundwater, become a part of the water cycle, and they stay there for a long time until like uptake by plants or us. And PFAS can even be found in very remote areas like Arctic, and they're detectable in surface and deep water in the ocean. And the wildlife in Arctic, like polar bears and foxes, the PFAS can be found in their body. Okay, that means PFAS has been like widespread and ubiquitous like in our environment today. And as we know, PFAS is used in many applications and is existed in many products surrounding us. So we can expose to it from many different sources. So in this figure, exposure can occur again via air, food, water, and even direct contact. But remember, the relative importance of different sources can vary dramatically across demographic groups and populations. And for ordinary people like us, the dietary intake of food plus water is the major source of PFAS exposure. And this is much higher than inhalation and the dermal contact. Okay. And drinking water can become a major exposure route if living close to contaminated sites. So as of today, some PFAS compounds are actually phased out since 2000 in the US, like Pfos and Pfoa. They're no longer manufactured in the US, but they are still produced internationally and can be imported into the US in some consumer goods. And you may have heard of the Stockholm Convention, which is an international environmental treaty to deal with persistent organic pollutants for restriction and elimination. So these two compounds, Pfoa and Pfos, they are included in in this treaty in 2009 and 2019. So we should anticipate gradually phase out of these two compounds worldwide. But however, the replacement chemistry was introduced because of the phase out. For example, the Genex and Adona replace a Pfoa, and the short chain compound like PFBS and other telomeres, they replace Pfos. And here you can see examples of their structures. So they're still fluorinated compounds, but some oxygen atoms connect to the carbon chain. And the question is, so are these compounds environmentally friendly? Are they less persistent and less toxic? That's something that we don't thoroughly understand yet. And then we should do research and monitor these alternative chemicals in the environment, maybe from now on. And we don't want to wait until a decade later and then find out they've been causing environmental and public health problems. Next, I'll talk a little bit about PFAS in humans. So we know PFAS have strong affinity to proteins, such as serum albumin. So they can be found in human blood. So the blood testing is widely used for evaluating PFAS exposure. So from CDC's nationwide survey, so here you can see Pfoa and Pfos concentrations in blood in different populations in the US. And apparently you see 3M and DuPont workers, they have the highest among others. And people living in communities with contaminated drinking water also have high levels of PFAS in their blood. And in general, the general US population shows relatively low concentration. in the blood, but still detectable. Okay, like it's like 3 orders of magnitude lower, but still detectable. Okay, and this one study actually showed measure like a Pfas in archive blood samples collected from 1957 to 2012, and they found Pfas in almost every sample collected during this period. And the only one sample that has no Pfas was collected from the Korean War era US military recruits. That's probably about like 10 years before the large scale Pfas commercialized production. Yeah. But the good news is that since 2002, and because of the phase out of PFOA and Pfos, so you can see the blood Pfas level in US population have gone down as well. But however, so as Pfos and PfOA are phased out and replaced, people may be exposed to other Pfas, which is a different chemicals. Yeah, so we need to keep monitoring it. Yep. And in terms of Pfas toxicity to humans, unfortunately, so toxicity mechanisms at the molecular level are not fully understood. So different toxic effects can occur at different places inside your body. So here's just one example. So if you recall the structure of Pfas compounds, they are pretty similar to fatty acids. So they might interrupt like this beta oxidation of fatty acid and then lead to an adverse effect in your body. So we know the Pfas is easily absorbed and widely distributed in human body. So they're stored in liver, blood, kidney, and muscle, and they can cross the placental barrier and excreted into breast milk. And they're slowly metabolized and are excreted in urine and feces. And in average, the biological half-life can up to 10 years, just pretty long. Yeah, and Pfas is are known to associate with all kinds of different toxicity, like neurotoxicity, reproductive toxicity, and like the cardiovascular toxicity. So as a result, they may lead to several disorders and diseases like in this figure, like kidney and breast cancers, liver damage, thyroid disease, and lower birth rate, something like that. Okay, and since the center is mainly focused on the water, okay, in this slide, I would like to show you EPA's third unregulated contaminant monitoring rule, so which was a nationwide survey in public water systems. So 6 Pfas compounds were monitored. So overall, Pfas was detected in about like 200 public water supplies, serving like 16.5 million people in 33 states and 3 American territories, like Guam and American Samoa, something like that. And about 6 million people exposed to Pfas contaminated drinking water. That was above EPA's health advisory level, 7 parts per trillion of PFOA and Pfos combined, okay? 7 ppt. And just give you an idea about the unit parts per trillion, it's just like a drop of water in a lake. That's very low, okay? And in New York State alone, and you can see a few public water supplies were contaminated by Pfas. And actually, most of them were somewhere on Long Island. Yeah, you can see the blue here. And some of this value like even exceeded the EPA health advisory level. You can see the Pfos can even go up to 530 parts per trillion. And please note that the UCMR3 only monitored public water systems serving more than like 10,000 people. Private wells and other sources have not been covered. Okay. And if you are interested in more recent data, you can check this website of Environmental Working Group. So there's an interactive map. You can search if there's a known contamination source near you. Okay, so you can see it's like as of July this year, over 2,000 locations are known to have PFAS contamination. Oops, sorry. Okay, so we know there's contamination issue out there, and what about guidance and regulations? And again, the US EPA has this 70 parts per trillion health advisory level, which is non-enforceable and non-regulatory, okay? And here in this map, by the way, this is not an electoral map, okay? So you can see several states, they have established their own standards and guidance values for PFAS. But this guidance could be for like groundwater, surface water, or drinking water. It varies from one state to another. Okay, the blue states. And the red states means to follow, okay, EPA health advisory level. And sorry for giving you this ugly table. So this table summarized guidelines and regulations in each state. So in this column, you can see the type of water they like focus, they regulate. And the point here is that almost every state set a standard for PFOA and PFOS, okay? And then followed by the PFNA C9 compound, PFHXS C6 compound, and PFBS C4 compound. And at the last column, you can see a few states began to monitor replacement chemicals like Genex. So you can see like Hawaii, this is Michigan, North Carolina, and Ohio, okay? They do something like this for the new replacement chemicals. And in New York State, we have a maximum contaminant level of 10 parts per trillion for these two compounds, PFOS and PFOA, and specifically in drinking water, okay? And this is the, not combined value, so individual value. So we have these two in New York State. Okay, and okay, from now on, I'm going to talk about the challenges in the detection of PFAS. So it might be a little bit technical, and hope I won't bore you, okay? So in order to measure PFAS in pp parts per trillion levels, so the sensitivity and precision are very critical. And as I said, there are over thousands of PFAS compounds in industry. But unfortunately, only a few of them have analytical standards available. So we can use them for identification and quantification. And some PFAS, they have structural isomers, and we need to be able to identify these isomers, because they might like behave differently. And like I said, the physical and chemical properties can vary a lot between short chain and long chain PFAS. So this would cause problems during sampling and sample preparation, okay? And as PFAS is used in so many products, we can easily introduce contamination during sampling, sample preparation, and even analysis. And how do we know if the value we measure is true? So we need certified reference materials for interlaboratory calibration. And unfortunately, the lack of CRMs available in the market, and we even have no CRMs for different sample matrices, okay? And at last, the analysis is time consuming and relies on expensive instrumentation. So liquid chromatography, okay, so the analytical methods for PFAS. So liquid chromatography with tandem mass spectrometry, LC-MS-MS, is considered the current standard instrument for PFAS analysis. And here you can see there are several methods for different sample matrices. And our lab currently adopts EPA method 537.1 and 533 for drinking water. Excuse me. And the setup of our testing facility was supported by New York State DEC, Department of Environmental Conservation, and New York State has an Environmental Laboratory Approval Program, ELAP, which is for the certification of laboratories performing environmental analysis on samples originating from New York State, and for ensuring the accuracy and reliability of this analysis. So in order to get this certification, the ELAP requires a series of performance evaluations and on-site inspections just to get the certification. And our lab is accredited by the New York State Department of Health for PFOA and Pfos analysis. Okay, and then it requires a detection limit of around like 2 parts per trillion. Yep. And here I just want to briefly show you how we process water samples. And because the PFAS concentrations in waters, in water is so low, so we have to use solid phase extraction to concentrate PFAS to detectable range. So here's an example. So we loaded water sample onto a specific resin to capture PFAS from the solution. And in the meantime, the interferences would not retain on the resin. And then we use a small amount of organic solvent to elute concentrated PFAS out. And by doing this, so we can bring the PFAS concentration several hundred times higher so that we can detect it. Okay. And here's the picture of our automated solid phase extraction unit. And during this process, we also add isotopically labeled PFAS compounds at different stages in order to evaluate recoveries of the sample preparation and also the performance of the analysis. So this is part of our QA/QC, quality control and quality assurance. And in this figure, you can see our LC mass spec in the lab. And once the sample is introduced into the instrument, okay, PFAS compound can be separated by the liquid chromatography. And each peak here actually represents 1 PFAS compound. And then the mass spec serves as a detector to identify and quantify each compound. So that's the simple principle of how it works, okay? And as we know, PFAS can be found in so many materials like Teflon. So we did several modifications on our instruments in order to remove any potential background contamination from the instrument itself. For example, there's no Teflon tubing allowed, on the instrument, and we have to remove this Teflon inline filter, and we have to bypass this degasser because a lot of Teflon material inside the degasser, something like that. So, and in this chromatogram, I just want to show you, for now, we are able to separate and detect 30 PFAS compounds. The combination of these two methods, 30 PFAS compounds from short chain to long chain PFAS, and including some replacement chemicals, telomers, and non-PFAS precursors. And we keep adding more analytes if possible. Okay, that's what we are currently doing right now. And in the next couple slides, and then I will quickly show you a series of our performance data. And the first is the isomer separation. So on the left, you can see an example of isomers. So you can see they have exactly the same molecular mass, but different chemical structure. And on the right side, you can see we are able to separate the branch isomer from linear isomer. And during the method development, so the 4 compounds were found to contain like branch isomers, like nephosa, methosa, the C6 compound, and C8 Pfos. So we are able to separate them, yeah, because the isomer is not like isotopes. The ratio between branch isomer and linear isomer can vary a lot, from one place to another. So we need to separate them and quantify them. Yep. And in this slide, you can see the PFAS background level in our instrument. So you can see very low system background, very clean. And our instrument is very sensitive. So we can even detect trace level of some PFAS compound like even in a high quality grade methanol. So you can see like tiny peak right here. Yeah, so our instrument is very, very sensitive. And we confirm our calibration using a second set of standards from the different vendors. And then you can see the result with is basically within the acceptable range. So 100% plus minus 30%. And we also tested our solid phase extraction method performance. So we added a known amount of PFAS in pure water and processed it through the extraction procedure and measure how much PFAS was recovered. And then you can see the recovery of each PFAS compound or between like 70 to 100% within the acceptable range. And we also calculated like how low we can detect. You can see our minimum reporting level right here is around 0.5 parts per trillion for each compound, like 0.5 parts per trillion. So it's much better than the MRL reported in the EPA method. And then all this data show that our lab can really do high quality trace analysis with accuracy and reliability. And next, I want to talk about the PFAS treatment technologies. Okay, so the activated carbon is actually a very commonly used sorbent to remove PFAS from water. So on Long Island, we use a granular activated carbon for water treatment for many other contaminants, including like PFAS. And the activated carbon, it uses hydrophobic interactions and can effectively remove Pfos and Pfoa. And it can also remove other contaminants simultaneously. And it is cheap, but it may need a frequent replacement. And it might have like early breakthrough for short chain PFAS compound. And the disposal might be an issue. Okay, I'll talk about that later. Yeah. And so ion exchange resin can also effectively remove both short chain and long chain PFAS with electrostatic interaction. So the PFAS is the compounds they are negatively charged. Okay, so they can enriched by this NR exchange resin. However, resins are typically more expensive and are one-time use, and they also have disposal issue. Okay, another approach is the membrane filtration, such as reverse osmosis. It is like actually a good point of use treatment method for PFAS. So with size exclusion and electrostatic repulsion, so short chain and long chain PFAS can be removed effectively. But the problem is that is to generate a concentrated waste stream and returning back to our groundwater or wastewater. And we have some ongoing projects related to absorption treatment. So we're going to test the PFAS removal by the different types of GAC, granular activated carbon, and evaluate the influence of water matrix and co-contaminants on the absorption capacity for PFAS. And we also collaborate with faculty in chemistry department to specifically focus on short-chain PFAS removal by biosorbents, such as cellulose, chitin, and cyclodextrin, or maybe other new polymers. So the idea is to design a sorbent that is low cost and high capacity for both short-chain and long-chain PFAS, and easy regeneration if possible. Okay, and like I said, although sorbent and membranes can remove PFAS effectively, and they don't destroy PFAS molecules, they just remove and concentrate PFAS to somewhere else. Okay, so that's why destructive techniques are important, because so we can actually break down PFAS molecule to smaller fragments and eventually turn them into CO2. Okay, the ideal case, okay. And we have an ongoing project using this high energy electron beam accelerator to break down PFAS. This work is collaborating with Fermi National Lab, And the principle for this electron beam is that the electron beam radiolysis can produce radicals and hydrated electrons in the solution. And the hydrated electron can break down PFAS molecules. So this hydrated electron, yeah, in a solution. And here you can see some of our preliminary data. So, and you can see as the electron beam dose increased, so more PFAS can be degraded. So it can go up to like 500 kilogray. It's pretty high, yeah. And we also tested whether the pH could influence the degradation efficiency for PFAS. And you can see a better degradation percentage at alkaline condition than acidic condition. And then we will be testing other water quality parameters, for this project in order to find out the optimal treatment condition. Okay, this is one of our ongoing projects. And there are more destructive technologies, including like plasma technology and electrochemical treatment. And we have an ongoing project collaborating with our industry partner to test a novel electrode to break down PFAS. So here's a picture of how the reactor looks like. So if electrochemical technology works for PFAS removal, and it would have a great potential for point of use or point of entry treatment, to remove PFAS. Yeah. And yeah, I think I speak too fast. Okay, at last, I have some general take-home messages for you. So, and we know PFAS can be found in many things surrounding us, and then we might expose to PFAS very frequently via diet, including drinking water. And to precisely measure PFAS is a challenge because the concentration in the environment is so low, and it can easily get contaminated, and other issues like such as like lack of analytical standards and reference materials. And the sorption methods work for PFAS removal, but they create waste to be handled further. So, and a few novel destruction technologies are being developed, but not yet available for commercial and municipal scale treatment. Yes, and oh, sorry. Okay, yeah. So this is the take-home messages, and at the end, I would like to thank our team members in CCWT and our collaborators, Fermi National Lab, Brookhaven National Lab, US EPA, and our faculties in the chemistry department and our industry partners, and also thank for our funding sources, the New York State Department of Health, DEC, and the Department of US Department of Energy. Yep. Thank you for your attention. So I'll take any question.
Cheng-Shiuan, if it's okay, I have a quick question.
No problem.
So I noted that, as you know, in the environment, there's many perfluorinated compounds, usually coexisting. And I note that some states, you put up some states like Texas and Hawaii, have regulations for many compounds, not just PFOS and PFOA. And so I guess my question is, obviously they wouldn't put up that regulation unless there was also health concerns with regards to those compounds. Mm-hmm. So I'm just wondering, it may be outside of your field, and I've asked Arjun about it as well, but I'm thinking about the extent to which these compounds may be having additive or synergistic effects. So clearly people are not being exposed to just one compound. Mm-hmm. And so if they're exposed to all of these, or more than one, or just 3 or 20, what are the biological impacts versus exposure to a single compound. And should standards, I'm wondering if the standards should consider adding up more than one compound as opposed to having one for each individual compound.
Yeah, that's a great question. Actually, in terms of the toxicity research, there are papers that showing this multiple PFAS compound can have a additive toxicity effect, but mostly PFOS, PFOA and PFOS, or some common compounds. And even I remember even some studies, they show like weak synergistic effect. So I would say that's possible. Yeah. So the toxicity can be like add up. Yeah. So.
Right. Yeah. Thank you.
Can I add something there? I just wanted to add, most of the toxicity data is on the C8s, right? The PFOA and the PFOS right now, because they're so abundant.
Mm-hmm.
And that's kind of the gold standard for our toxicity tests now. But that doesn't necessarily mean they're the most potent. They're really just the most abundant, right? So the relationships with chain length and the way that they influence absorption onto different proteins and things like that, those are all chain length dependent, and there's still a lot to tease out about the relative potency. Additionally, there was a really good review that came out recently by Gloria Post from New Jersey Department of Environmental Protection, I think, about how all these states are getting their different standards. So that would be a good place to look if you want more information about why different states have different regulations.
Thank you so much, Carrie.
I also have a question. So
sure.
With your the new exciting treatment technologies, I was wondering if there's data from a mass balance to see that the compounds you're degrading are completely degrading to their CO2, final end products or not.
That's a great question. That's something that we want to do. Yeah, but I believe we need something to measure like total, like maybe like organic fluorine or inorganic fluorine, just like a combustion ion chromatography, something like that, in order to do the total fluorine. And you can see our LC triple quad, actually, we can only do like target compound, and we need like a LCQ top to do those like unknown PFAS fragments, something like that. But that's something we really want to do. Yes, you're right. The mass balance is extremely important. Exactly. Yeah.
Just to add, so this is Arjun Venkatesan, and I just want to add to what Cheng-Shiuan said. Yes, so we haven't completely optimized these new technologies yet. So we are observing degradation of these targeted compounds like Pfos and PFOA, maybe up to 40–50% degradation. So interestingly, what we're noticing is when we run the EPA method, which covers for a wide range of analytes, we're not seeing any detection of short chain compounds. So certainly there are other organofluorine compounds that are not short chain version, or maybe it's mineralizing partly to carbon dioxide and fluoride ions. But it's been a little tricky for us to do a mass balance. But Cheng-Shiuan is right on the spot. It might be worth looking at QTOF analysis to look at what other products might be forming here.
Mm-hmm. Okay. Any questions?
There are questions in the chat.
Okay. Oh, okay. So Jian has a question. What's the level of blank contamination of the equipment? Okay. So we can so if we try, we can see a peak if we convert that to the concentration. It's about at the like a 10 like low nanogram per liter level, something like that. Yeah. And can you, Sam has a question. Can you talk a little bit more about disposal method for concentrated waste? Oh, yeah, so for the GAC, so we just, incinerate those GAC. Yeah, that's probably the most commonly way to do that. So we just destroy everything, every organic compounds on the GAC using the high temperature. Yeah. Okay.
Yeah, so just to add to that, Cheng-Shiuan, so incineration is the typical way of disposing GAC that's been exhausted. There are some regeneration facility who try to reactivate the carbon to reuse them. But what research has shown that the incineration process to dispose of GAC does not mineralize PFAS completely. And some of the PFAS that is associated with GAC is released back to the atmosphere, unfortunately. So it's not the ideal way of disposing GAC that's contaminated with PFAS.
Yes. Okay. So any more questions?
Nice talk, nice work. Thank you.
Oh, thank you, Bruce.